Hey, we're going to start looking at derivatives, but as we go in that direction, we want to talk about slope just for a little bit. So when we talk about slope, to start with, usually we start thinking about slope as part of a straight line as a rate of change. And in the straight line, the slope is constant. By that we mean we go up and over the same amount no matter where we are. That constant rate of change, or that constant slope, is what gives us the straight line. Okay, but when we start talking about a curve, then we see something different. So right here I've got x squared, and if I take a point on x squared, such as when x is 1, if I want to go over 1, if I want to go over 1 and up some, it looks like the first time I do that, I go up about 3. And then if I go over 1 again and go up, it looks like I go up about 5, I believe, because I'm going from 1 to 4 to 9. Yeah, so this slope here, where this rate of change went over 3 up 1, and no, went up 3 over 1, and the next one went up 5 over 1. So the slope was different at different places. Okay, so we can't expect to say that one number will define how this function is changing as we move across it. So we'd like to be able to quantify how fast something is changing at different points. And since it's a different than a straight line, it's an actual curve, it will be different values. Okay, so let's see where we can go with that. Okay, let's reimagine the slope formula. So remember the slope formula, if we were given 2 points, x1, y1, x2, y2, we found the difference in y's over the difference in x's, and that works very well for the straight line. Okay, let's use the same concept for finding slope, a change in y over a change in x, but let's write it in a function notation. So let's imagine we have a point where we have the x value and we plug the x value into the function to get the y. So here I have x and f of x, which is just like x1, y1. Okay, it's just one singular point, just defined or written a little bit differently. And then instead of creating a new variable like an x1, x2, let's say that we're just going to move off of that original point some amount, h. So I was at x, now I'm moving over to x plus h. So we're not going to define how big h is right now. We're just saying we're moving over some amount. And so if the input is x plus h, then we're moving over, up to f of x plus h. So we're plugging that new x value in. So more or less, if I drew myself a little graph here to kind of represent, let's get back here, all the way to the top of the page. Okay, so if I'm going to draw myself a little graph to show you what's going on here, what we're saying is we're going to have an x and y axis. We're going to pick a point, x, and it has a height of f of x. Okay, so that gives me a point. And then I would follow that curve to another point that would be h distance apart. So I come over here to x plus h. And when I plug that into a function, I get f of x plus h. Okay, so we're just saying we got 2 points. Now keep in mind, we haven't defined how big h is. So those points could be really far apart or they could be really close together. And the question is going to be, do they need to be close or far for it to be a good representation? So I'm going to come down to the x squared graph again. And let's look at the point when x is 2. So why did I pick 2 here? Okay, so when x is 2, we got the y value of 4. So let's make ourselves a little table here. Okay, x is 2. We'll make this x and we're going to make it a y. So we'll have 2, 4. and that point we're always going to use. Okay. But then if we want to pick a different point, we can move over to 3, which would be 3, 9. And if we pick that slope, as we said, that would be 5 change for y and 1 change for x. So the slope would be 5 coming off of that 2, 4. But what if I use that 2, 4 and went over to 4, 16. 16 is 4 squared. That slope would be 16 minus 4, which would be 12, and 4 minus 2, which would be 2. So that slope would be 6. So I went further away from the point where x is 2, and I got a different slope. Now, right now, we don't know if that's more accurate or less. But what if we pick something really, really close, like 2.1? Okay. So if I pick 2.1 and I square it, I get 4.41. So in that case, if I find the slope between those 2 points, I would have 4.41 minus 4, that'd be 0.41, and on the bottom I'd have 2.1 minus 2, that'd be 0.1. So let's see, 0.41 divided by 0.1 gives me 4.1. So picking a point really close to it probably means it has about the same slope or the same rate of change as the other point. So we've moved much closer, and we've got something close to 4. We moved further away, and I believe this number will keep getting larger. So in actuality, if we want to take 2 points, whatever they might be, and use them to calculate the slope at a point, we probably want those 2 points to be very, very close to each other. Okay? So kind of like I used the 2 and the 2.1. Because when the distance is small between them, it gives you a good indication of how the y value is changing. But how close can we get? So let's see what that is. The closest we can get is what we call the derivative here. And it takes the same thing I just did. The x, let me write this in here and then we'll take it out, but x plus h minus x on the bottom. So you still see the point here, x and f of x, and you still see the x plus h, f of x plus h. But we want that h to be as small as possible. And when we do that, because the x minus x on the bottom cancels out, we're just left with h. We can't exactly make it 0 on the bottom. Okay? So what we're going to do is we're going to use that limit idea and let h get close to 0. And what this is going to do is it's going to give us a function. And usually our naming notation here is we'll call this f prime or g prime based off of whatever the original function is, or if our original function is y, we'll call it y prime. And the name we give for this is the derivative, which will calculate the slope, or rate of change. So we're going to see this function used here in just a second on one example, and then another example. I might just save it for the second video. But what we're talking about is taking 2 points and getting them as close to as possible together. So that means they're going to be virtually the same point when we let h, which is the distance between the two, be 0. So in doing this, what we're going to calculate is something called the derivative, and it will tell us the slope anywhere along that curve. It's going to be a function itself, which means that we can use it to calculate the slope at different points. We'll pick an x to plug in, and we'll calculate a slope. So let's save that for the next video, a couple examples.